You've seen them a million times, right? The zebra's stripes. They're probably one of the most famous patterns in all of nature. But have you ever stopped to really think about why they have them? I mean, why would an animal trying to hide on the savannah paint a giant target on its back? Well, for centuries, that's been a huge mystery. But today, we're going to dive into the science and finally solve this incredible riddle. So, the big question really boils down to three main theories. The usual suspects, you could say. First, were the stripes some kind of crazy camouflage to confuse big predators like lions? Or maybe it was a clever form of air conditioning, a way to stay cool. Or, and this is where it gets interesting, was the real enemy something much smaller and way more annoying? We're going to investigate all of them.
And you know, this isn't some new debate that just popped up. Nope, this riddle is old, like really old. It goes all the way back to the guys who basically invented evolutionary theory.
I'm talking about Darwin and Wallace themselves. Can you believe it? Even they couldn't agree on this. Wallace was all in on the camouflage idea. But Darwin? He was super skeptical. He just thought, no way, these things are way too flashy. And that disagreement, right at the very beginning, kicked off more than 100 years of scientific detective work.
Now, what makes this whole puzzle even harder, or maybe more interesting, is that not all zebras are striped the same way. It's not one size fits all. You've got your plain zebra, which is pretty common and has variable stripes. Then there's the Grevy's zebra with these super narrow, dense stripes. And finally, the mountain zebra with its bold pattern. This variation is a massive clue. It's basically nature telling us that a single, simple answer, yeah, that's probably not going to cut.
Okay, so let's get into it. We're going to start by tackling the classic theories, the big ideas that everyone's heard of. And first on the chopping block is the one you've probably thought of yourself: camouflage.
Right, to really test this camouflage idea, we have to stop thinking like humans. We have to try and see the world through a predator's eyes. So on the left, that's our view, sharp, clear, full color. But look at the right. That's what a lion or hyena sees. Their vision is way less detailed, and they're basically colorblind to reds and oranges. What that means is, once you get more than about 50 meters away, those sharp black and white stripes they blur into a solid block of gray.
And that right there is the key. By the time a lion is close enough to actually see the stripes clearly, it's way too late. It already knows lunch is on the menu. At the distances where predators are actually scanning the horizon for a meal, the stripes don't help the zebra hide at all. So we can pretty much put a big red X through the camouflage theory. It's just not the main reason.
Okay, so camouflage is out. What about staying cool? This next idea is, well, it's pretty clever. It's called the cooling eddy model. The thinking goes like this. Black stripes absorb more sunlight, so they get hotter. White stripes reflect light, so they stay cooler. The theory was that this temperature difference would create tiny swirling air currents, little mini vortexes, right on the zebra's skin. It's like having your own built-in personal cooling system. A really beautiful, elegant idea.
But, and you knew there was a but coming, right? When scientists actually tried to test this, they ran into a problem. They found zero evidence of these stable cooling currents. Turns out, the slightest puff of wind, or even just the zebra moving, would totally wreck any little air current that was trying to form. So that beautiful theory? Yeah, it just didn't work in the real world.
Okay, but hold on, because this is where the plot thickens. Even though that specific cooling model was wrong, scientists still found a really strong link. The hotter the place a zebra lives, the more intense its stripes are. So, temperature is definitely part of the story, but the connection is way more complex than just mini fans on their skin. And this little puzzle? This is the clue that leads us to the real answer.
So, the big breakthrough finally came when researchers shifted their focus. They realized the biggest, most constant threat to a zebra wasn't a lion's powerful jaws. It was the bite of something way smaller, and honestly, a lot more persistent.
And this is it. This experiment basically cracked the case. Just look at this. When biting flies, like horseflies, go to land on a horse, it's easy peasy. They slow down, they have a controlled approach, they land, they bite. But look what happens with a zebra. The flies come in hot, at full speed, but they can't seem to slow down. They either crash right into the zebra, or they have to swerve away at the last second. Their landing success rate is terrible. The stripes are basically a high-tech anti-fly landing system.
So what is going on inside that little fly's brain? Let's break it down. It sees the zebra and zooms in for a landing. But as it gets closer, the stripes just completely mess with its vision. It's like its internal GPS just gets totally scrambled. It can't figure out how close it is or how fast it's going, so it never hits the brakes.
And the result is a total catastrophe for the fly. It either smacks right into the zebra or has to bail out. So, why does this happen?
Well, the first reason has a fancy name, the aperture effect. But it's actually pretty simple to understand. You know how when you look at an old-school barber pole, the stripes look like they're endlessly climbing upwards, even though the pole is just spinning in place? The zebra stripes create that same kind of illusion for the fly's eye. It's a chaotic mess of false motion signals, and the poor fly has no idea which way the zebra is actually moving or how fast.
And there's a second weapon in the zebra's arsenal, something called spatiotemporal aliasing. Okay, that sounds complicated, but think of it this way. A fly's eye has a certain frame rate, just like a camera. If the stripes move past its eye too quickly, it's like the video gets all choppy and garbled. It's just visual gibberish. The fly's brain is totally overloaded and can't calculate distance anymore. And that's exactly why it can't slow down in time.
And get this is not just some random lucky side effect. This is evolution at its most brilliant. The width of the stripes, especially those really narrow ones you see on a zebra's head and legs, they are almost perfectly tuned to the exact limitations of a fly's eye. It's like they're precision engineered to create the absolute maximum amount of confusion.
Okay, so the case against flies is looking pretty solid, right? They seem to be the main reason for the stripes, but the story doesn't end there. The zebra's coat is even cleverer than that. It's not just a one-trick pony, it's a true masterpiece of multitasking.
The thinking now is that different stripes on different parts of the body actually do different jobs. So those super narrow stripes on the head and legs, those are for the flies. They're the anti-fly landing system. But the bigger, broader stripes on the main body, well, those might actually be for the lions after all. They create something called motion dazzle that can confuse a predator that's in hot pursuit. And the stripes on the back end, they've got their own special job too.
This part is so cool. So those big, bold stripes on the rump, during a chase, they're the most eye-catching part of the whole animal. And the theory is that they're designed to be. They draw the lion's attention to the rear end of the zebra, which, conveniently, is the furthest point from the vital organs, and it's the part that can deliver a kick powerful enough to shatter a jaw. It's literally a tactical defense system painted right on.
So, we've pretty much nailed down the why, but that leaves another huge question: how? How in the world does a developing zebra embryo actually create a pattern this perfect? Well, the answer, amazingly, comes from the world of math and genetics.
The whole process is described by something called a Turing pattern. Yeah, as in Alan Turing, the famous mathematician and computer scientist. Way back in 1952, he figured out, mathematically, that if you have two simple chemicals, one that turns on a process, an activator, and one that shuts it off, an inhibitor, they can interact to spontaneously create all sorts of complex patterns, including stripes. And that elegant mathematical idea is exactly what's happening in a baby zebra's skin.
And what's really incredible is that today, we're actually pinpointing the exact genes that do this work. We're finding the genes that act like the master switch, turning color on and off. We're finding the ones that control how wide or narrow the stripes are. It's like we're finally reading the source code for the stripes, the very genetic instructions that Turing's math predicted all those years ago.
So, let's wrap this all up. The real answer to why do zebras have stripes isn't some simple one-line answer. It's so much better than that. The stripes are a multi-tool, an evolutionary Swiss Army knife. They're a high-tech weapon against disease-carrying insects, they're a tactical defense system against predators, and they're part of a complex answer to surviving life in the African heat.
You know, it took scientists more than 100 years of arguing and testing to finally figure out this one pattern, which really makes you wonder, right? If this is the incredibly complex, brilliant story behind something we all thought was so simple, how many other amazing secrets are still out there, hiding in plain sight, just waiting for us to look a little closer and ask the right questions?